Hello students, welcome to another video of calculus. Today in this video we will continue the remaining part of the theorem which we have discussed in the previous video. So the B part of the previous theorem is if the sequence yn is bounded sequence and a bounded decreasing sequence, then we have to prove that that sequence converges to its infimum. So in the second part we have given if y is equals to yn be a bounded sequence which is decreasing, that is bounded decreasing sequence, then we can write sequence x is equals to minus of y. This sequence is bounded decreasing, and if you multiply that each and every term of that sequence by -1, then we get increasing sequence, that is minus y means minus of yn for each n, that is minus of every element of this sequence, and this sequence is again bounded increasing sequence, this sequence is bounded increasing sequence. Therefore, and for the bounded increasing sequence, in the first part we have proved if the sequence is bounded increasing, then that sequence converges to its limit. Therefore, by part A we can write limit n tends to infinity. So sequence xn, limit n tends to infinity, sequence xn, here xn is the sequence of bounded which is bounded increasing sequence. Clearly this minus y there, that is minus of yn is bounded increasing sequence. So by part A we can write limit n tends to infinity, sequence xn is equals to supremum of this minus of yn, because x is equals to xn is equals to minus yn, supremum of minus yn such that n belongs to set of natural numbers, Now here limit n tends to infinity xn, limit of this sequence xn is equals to minus of limit n tends to infinity sequence yn, the limit of sequence yn. Therefore we can write supremum of minus of yn such that n belongs to set of natural number. Supremum of this minus yn is equals to infimum of this sequence yn. Supremum of this minus of yn means supremum of this sequence xn is equals to infimum, minus of infimum of that xn is equals to minus of infimum of yn such that n belongs to set of natural numbers. Supremum of this minus yn is equals to minus of infimum, because the sequence yn is bounded decreasing sequence. Bounded decreasing means this sequence has infimum. Now we have taken x is equals to minus of y, that is minus of yn, then this sequence is clearly bounded and increasing sequence. So bounded and increasing means that sequence converges to its supremum. Supremum of minus yn is equals to minus of infimum of yn, because we are multiplying by -1 to each and every term of that sequence yn, then that sequence become increasing bounded sequence. So supremum of minus yn is equals to minus of infimum of yn. So supremum of minus yn is equals to minus of infimum of yn. Therefore limit n tends to infinity, therefore limit of sequence yn, limit n tends to infinity sequence yn is equals to minus of limit n tends to infinity sequence xn, and which which equals to this minus of limit n tends to xn is equals to infimum, limit n tends to infinity xn is equals to minus of limit n tends to infinity yn, and the limit of that yn is equals to infimum of the sequence yn such that n belongs to set of natural numbers, because the sequence xn converges to, that is the limit of sequence xn is equals to minus of limit of sequence yn, and the sequence as the sequence converges to its supremum of minus yn. So supremum of minus yn means in minus of infimum of yn. So we can write limit n tends to infinity yn is equals to minus of limit n tends to infinity xn, and this limit is equals to infimum of yn. So hence the limit of sequence yn is infimum, that is the sequence which is decreasing and bounded sequence converges to its infimum. Therefore, we can write limit n tends to infinity yn is equals to its infimum of yn such that n belongs to set of natural numbers. Hence, the proof of second part. In this second part, we have to prove the sequence yn is bounded decreasing, then that sequence converges to its infimum. So, we have taken x is equals to minus of yn. So, as the sequence yn is bounded decreasing, so minus of that sequence is bounded increasing sequence, and for the bounded increasing sequence we have seen in the first part of this proof that limit n tends to infinity, that sequence y bounded increasing sequence converges to its supremum. Now, limit n tends to infinity, xn converges to supremum of minus of yn. Xn is minus of yn, so its supremum, but supremum of minus yn is minus of infimum of yn. So, we can write this limit n tends to infinity xn is equals to minus of limit n tends to infinity yn, and the supremum is equals to minus infimum. We have to prove the limit n tends to infinity of yn, as this limit n tends to infinity of yn is equals to minus of limit n tends to infinity xn, and limit n tends to infinity xn is this supremum, and supremum is equals to minus infimum. If we multiply, minus of minus become plus. So, limit n tends to infinity yn is equals to this infimum. Hence, the proof of second part of this monotone convergence theorem. Now, we will discuss one example on this. So, the example is, using this theorem we can find the limit. So, the first example is, let x1 is equals to 1, let x1 is equals to 1 and xn plus 1 is equals to square root of 2 plus xn, square root of 2 plus xn for n belongs to natural numbers, for n belongs to natural numbers. Show that this sequence xn converges, sequence xn converges, and find the limit, and find the limit. Now, to solve this example, we will use the previous theorem, which is monotone convergence theorem. So, using monotone convergence theorem, we have to prove that this sequence is bounded sequence, and this bounded sequence implies that sequence converges. So, for the boundedness, we have given that x1 is equals to 1, let x1 is equals to 1, and for the remaining elements of the sequence, we have given the formula xn plus 1 is equals to square root of 2 plus xn for n belongs to natural numbers. Now, our claim is this sequence is increasing sequence. First of all, we will prove this sequence is increasing. Sequence xn is increasing. Sequence xn is increasing. That is, we have to show that xn plus 1 increasing means the next element is greater or equal to the first one. So, xn plus 1 is greater or equal to xn for all n belongs to natural numbers. So, we have to prove that the sequence is increasing. Now, for n is equals to 1, we have x1 is equals to 1, n is equals to 2, we can get square root of 2 plus 1. For n is equals to 3, we get square root of 2 plus that x2. So, for n is equals to 1, 2, 3, the terms of the sequences, we can find the terms of the sequences. Now, for n is equals to 1, 2, 3 and so on, the terms of the sequences, the terms of the sequence are, so for n is equals to 1, we have x1 is equals to 1, and for the remaining we have square root of 2 plus x1. So, 2 plus 1 is 3. Now, for the next term, we get square root of 2 plus x2, and now x2 is square root of 2 plus 1 is 3. So, square root x is 3, root 3 and so on. So, first term is 1, second term is square root of 3, third term is square root of 2 plus root 3. The next term will become 2 plus square root of this term, whole term, 2 plus square root of root 3 and so on. These are the terms of the sequences. So, clearly we can say that this 1 is less than or equals to square root of 3, because so clearly 1 is less than 3. 1 is less than 3 implies square root of 1 is 1 is less than square root of 3, as 1 is less than 3, and if you take the positive square root, then square root of 1 is 1, square root of 3 is root 3. So 1 is less than square root of 3. This implies our x1 is less than x2. So clearly, similarly for the next terms, we can write x2 is less than x3, and so on up to we can write xn is less than xn plus 1. Similarly, if you take root 3 and 2 plus square root of 3 and taking square on both sides, we get 3 is less than 2 plus root 3. Root 3 is again 1.141 something, and if we add 1.41 into the 2, then we get 3.41 something. So 3 is clearly less than 3 point something. So x2 is again less than x3. Similarly, all the other terms xn is less than xn plus 1. This implies xn plus 1. Xn plus 1 formula for the xn plus 1 is given as square root of 2 plus xn. This is the formula, and clearly this is less than square root of 2 plus xn plus 1. 2 plus xn plus 1, that is xn plus 2. So all the first term, that is xn is less than xn plus 1. So similarly xn plus 1 is less than xn plus 2. Xn plus 1 is less than xn plus 2. So by induction we can write the xn is less than xn plus 1 for all n belongs to set of natural numbers. So this implies our sequence xn is increasing, implies sequence xn is increasing sequence. The sequence is increasing sequence. Now as we observe that the first term of the sequence is 1 and the sequence is increasing, so sequence is clearly decreasing, that is sequence is clearly bounded below. First term of the sequence is 1 and all other terms are greater than 1, so clearly this sequence is bounded below. So as the first term of the sequence, as the first term of the sequence is 1 and the sequence xn is increasing and sequence xn is increasing, hence it is bounded below, because first term is 1 and all other terms are greater than 1, so clearly it is bounded below. Clearly it is bounded below, that is all the terms of the sequence xn are greater than or equals to n for n belongs to set of natural numbers, because the first term is 1 and all other terms are greater than 1, so this sequence is bounded below, that is 1 is the lower bound of that sequence, so this sequence is bounded below. Now we have to show that this sequence is, since we have seen that sequence is increasing, again we have seen that the sequence is bounded below, we have to, if this sequence is bounded above, then we say that this sequence is bounded, that is sequence is said to be bounded whenever sequence is bounded below as well as sequence is bounded above. Here we can say that sequence is bounded below. If the sequence is bounded above, then we can say that given sequence is bounded, and every bound in the monotone convergence theorem says that if the sequence is monotone and bounded, then sequence is convergent. So we can say that this sequence converges. So we have to show that xn is bounded above. Now our second claim is, now we have to show that, now we show that sequence xn is bounded above. Sequence xn is bounded above. Sequence xn is bounded below because all the terms of the sequence are greater than or equals to 1. 1 will become lower bound, so sequence is bounded below. But for the sequence is to prove the sequence is bounded above, there is no, that is we can say that by observation, we have to prove by using mathematical induction. We prove this by mathematical induction. By mathematical induction. Mathematical induction means we have to prove for n is equals to 1, and suppose for n is equals to k, and prove for n is equals to k plus 1. For n is equals to 1, we have x1 is equals to 1 and this 1 is suppose less than or equals to 2, because we observe that 1 plus root 3, root 3 is less than 2, square root of 2 plus root 3 is again less than 2, square root of 2 plus root 3 again less than or equals to 2. So our sequence lies inside 1 and 2. So here this 1 is less than or equals to 2. So here 1 is clearly less than 2. So our for the first term, first element is less than or equals to. We will suppose that result is true for n is equals to k. Now this in the second case of, in the first for n is equals to 1, we get result is true. Now assume that the result is true for n is equals to k. The result is true for n is equals to k, that is xk is less than or equals to 2 for all k belongs to natural numbers. For instead of for all, just write some for k belongs natural numbers. For k belongs natural numbers. Now to prove the result is true for n is equals to k plus 1. Now to prove result is true for n is equals to k plus 1. Now consider the x k plus 1. Consider x k plus 1. X k plus 1 means by the formula we have 2 plus xk, square root of 2 plus xk. Now the square root of 2 plus xk. So by the second part we have xk is less than or equals to 2. So we can write this is less than or equals to square root of 2 plus xk is less equal to. So square root of 2 plus 2, 2 plus 2 is 4, and square root of 4 is equals to 2, which is equals to 4. So this implies xk plus 1 is again less than, square root of 4 is equals to 2, xk plus 1 is less than or equals to 2. This implies xk plus 1 is less than or equals to 2. Hence the result is true for n is equals to k plus 1. Therefore the result is true for n is equals to k plus 1. Therefore by principle of mathematical induction, result is true for all n belongs to set of natural numbers. Result is true for all n belongs to set of natural numbers. Hence our sequence is bounded above. Therefore the sequence xn is bounded above. Sequence xn is bounded above as well as bounded below, implies sequence xn is bounded sequence. Sequence xn is bounded sequence. Hence we get this sequence xn is monotone bounded sequence. Monotone means sequence is either increasing or decreasing. We have proved the sequence is increasing and bounded. Hence sequence xn is bounded monotone sequence. Bounded monotone sequence. Hence this sequence is convergent. Hence sequence xn is convergent by using monotone convergence theorem. This sequence is convergent by using monotone convergence theorem. Now we have to find the limit of this sequence. Suppose sequence xn converges to L. Sequence xn converges to L. Now if the sequence xn converges to L means limit n tends to infinity of that sequence is equals to L. Now we will consider the limit n tends to infinity of sequence x n plus 1 for the n plus 1 term, which is equals to limit n tends to infinity sequence xn, because for limit n tends to infinity xn plus 1 and limit of the sequence is unique, so limit of xn and xn plus 1 xn plus 1 are same, so limit n tends to infinity xn. Now the xn will be square root of 2 plus xn and limit n tends to infinity xn is equals to l. So using the both we can write this limit n tends to infinity xn plus 1 means square root of 2 plus xn, which is equals to limit n tends to infinity xn. Now limit n tends to infinity, so square root of 2 plus xn, so we can write square root of 2 plus limit n tends to infinity xn, and limit n tends to infinity xn is equals to l. So substituting the limit n tends to infinity, we get 2 plus limit n tends to infinity xn is l is equals to limit n tends to infinity is again l. So squaring on both sides, we get 2 plus l is equals to l square, and now just rearranging the terms, we get l square minus this l minus 2 is equals to 0. This is the quadratic polynomial, and to find the roots of this polynomial, we get l, that is 2 minus 1, sorry 2 and plus 1, 2 into 1 is 2 and minus 2 plus 1 is minus 1, so l minus 2 l plus 1 is equals to 0. So there are two possible values of l, either minus 1 or 2, but the sequence is bounded and sequence lies in between 1 and 2, so limit of that sequence must be 2, not 1. Therefore the sequence, given sequence is sequence of real numbers, all the terms of that sequence are positive, bounded above, and that sequence is in between 1 and 1 and 2, so the limit of sequence of xn is equals to 2. This sequence xn, there are two possibilities, minus 1 or 2. The sequence xn is of the sequence xn is of the sequence of positive real numbers, and bounded above. Then it will never converges to minus 1. So sequence of positive number that will not never converges to minus 1. Bounded above, then it will never converges, or it will never converge to minus 1. Therefore limit of that sequence is 2. Hence limit n tends to infinity xn is equals to 2. Limit n tends to infinity xn is equals to 2. Hence the solution of the given example.